Thank you very much. Thank you very much for the invitation, Michael. So I first of all want to thank all the co-authors that are listed here and that greatly contributed to the new results and the records from polar ice core that I will present to describe the millennial-scale climate variations during marine isotopic stage 5. So first of all, well, you probably all know the period of marine isotopic stage 5, but just a summary. So marine isotopic stage 5 is characterized by relatively strong variation in precision, I mean compared to the rest of the glacial period, following glacial period. From the marine records, so benthic, delta weighting, or coral reef, we know that marine isotopic stage 5 is characterized by high sea level, and especially during marine isotopic stage 5E, we can have a higher sea level than today. And from the polar ice core, so here is the delta D record from the East Antarctica Downscale ice core, we see that again during marine isotopic stage 5 we have very high value of delta D, and this suggests actually that stage 5E was warmer, at least in the polar region, by let's say 2 to 4 degrees in Antarctica at that time. It's very nice to study marine isotopic stage 5 from polar ice core because first of all we will have several ice cores that will cover this time period from Greenland and from Antarctica. And the second thing is that we can have a relatively high temporal resolution. So even for this Downscale East Antarctica ice core with very low accumulation rate, we can have down to 20 years resolution. So the outline of my talk is the following. First, I will show you the existing records from Greenland and Antarctica that cover marine isotopic stage 5. Then I will focus first on the Greenland records, showing you the temperature reconstruction over that period using delta 59 and delta 40 argon in the air trapped in ice core. Then I will detail you the methane record with some high resolution. And I will show you as well the millennial-scale variation in atmospheric delta weighting from the Greenland records. Then I'll do the link with the Antarctic record using both methane and atmospheric delta weighting to obtain a common timescale, and this will enable to describe the seesaw behavior during marine isotopic stage 5. And finally, I will compare some Antarctic records over marine isotopic stage 5 and show you some temperature reconstruction from combination of delta D and the excess in ice core. So the Greenland records, and that is a map that Rob Mulvaney already showed yesterday with the location of the numerous ice core that we have in Greenland. And here you have all the, well, not all the records, I forgot Rhineland for example, the ice delta weighting record on a depth scale. The first record that was recovered from Greenland were, for example, Camp Century and Dice 3. So you have the location here, Dice 3 and Camp Century. And if you look at the bottom part of those ice core, you see that we have relatively high ice delta weighting for both. And actually, this plateau of ice delta weighting probably is ice from marine isotopic stage 5. And if you compare to the present day level, that is here with the gray line, you see that it's clearly higher, again suggesting that temperature was higher in Greenland at that time, and probably part of this temperature change is also linked to a change in elevation. The problem is that we cannot really use those records to discuss the climate variations in Greenland because we can have problem with stratigraphic disturbance at the bottom of those ice cores, and that's why we try to use more recent ice core. So here you have the record for the Grip and Gisp 2 ice core that were drilled 30 kilometers apart at the summit of the Greenland ice sheet, and you see that for the, so those ice cores show actually very similar record back to 90 kiloyears before present, but you see that for the bottom part of those records we have a very strong disagreement in the ice delta weighting record, and of course those rapid variation in ice delta weighting are not due to climate variations, but linked to stratigraphic disturbance. Still, you can see that we have very high ice delta weighting value, both in the GRIP and in the GISP to record, and it could be shown that those ice section corresponds to ice from marine isotopic stage 5e, and again you see that it's higher compared to the present day level, so again we suggest a higher temperature. So finally, we are left with only one Greenland ice core that record marine isotopic stage 5, but unfortunately, we cannot record the full marine isotopic stage 5, so as you can see here, we have only the end of 5e and then the glacial inception with rapid climate variation occurring very early during this glacial inception. So that's from Greenland. Now let's go to Antarctica, and here we are more lucky because we have several ice cores that record marine isotopic stage 5. So the first one was Vostok. So here you have the delta D record on depth scale, and you see the general variation during 5e, so with a climate optimum, again, so very significantly higher than the present day level, and then a plateau, and then we go into 5D and 5C. This record from Vostok in East Antarctica was confirmed then by the Dome F record. So you see here almost the same pattern during 5E, and we find almost the same as well on the Dome C East Antarctica ice core. So for the plateau, we have exactly the same, let's say, climate variation. However, if we look at other ice cores that also record marine isotopic stage 5, we can see some differences. So for example, here you have the EDML ice core. So almost here, and you see that the climatic optimum here is much less marked, and we have more like a plateau. Well, here we are not so sure that it should be interpreted in terms of different climate trend, because for the EDML ice core, we have to be concerned by the fact that this ice core was drilled on the slopes, so probably there is here the problem of ice coming upstream. And finally, I just wanted to show you some very recent results from the Talos ice core, and that is here. And here you see very interestingly that we have, again, this climatic optimum, then it decreases, but here it increases again. And so here we have to explore that a little bit more, but that could be a problem, perhaps a change during that period of the source of the precipitation in Antarctica. So now let's come back to Greenland, and I will show you the temperature reconstruction over marine isotopic stage 5. So when we want to reconstruct temperature in Greenland, we do not have to use the ice delta weighting. It's not a quantitative marker because it's affected by the source of the precipitation and the seasonality of the precipitation. So what we will do is that we will use the isotopes of nitrogen and argon that are trapped in the air bubble in ice core. So we do that because delta 59 and delta 40 argon, they do not show change in the past atmosphere, so that the variation that we will record in the air bubble are linked to physical fractionation in the firn, that is to say the upper, let's say, 100 meters at the top of the ice sheet constituted of porous snow. So what are those physical fractionations? So you can see them directly here on delta 59 and delta 40 argon measurements on the firn. First, you have here this line that is the results of a gravitational signal. So simply because of gravity, we will have more heavier isotopes at the bottom part of the firn, but that is not very interesting to reconstruct past temperature. What is more interesting is to use what happens here, and which is actually the result of a thermal signal. So indeed, if you apply a temperature gradient to a gas mixture, you will observe that the heaviest isotopes, they will go toward the coldest end of this gradient. And that's the case here because, well, the gas sampling was done during the summer, so the top is warm, and here it's cooler, and we have indeed this increase in delta 59 and delta 40 argon. So we do not aim to reconstruct seasonal temperature with the delta 59 and delta 40 argon trapped in ice core, but we will have this thermal fractionation when we look at Downscale even, and that was first shown by Jeff Suringhouse at the Scripps Institute. So indeed, when we have a rapid warming, we will have at the top of the front a warm temperature. Here it will be still cool, and we will have over the entire front a thermal fractionation so that our delta 59 and delta 40 argon will increase in the air bubble. So that's exactly what we obtain when we look at the gas record. So here you see again the ice delta 018 record from the North Grip ice core with the third Downscale event 25 very soon during marine isotopic stage 5, 24, 23, 22, and 21. And you see here at the top the delta 59 and delta 40 argon high-resolution measurements. And you see that for each rapid warming that you record in the ice delta 018, you have a peak in the delta 59 and peak in the delta 40 argon. Then you can use those measurements combined with a fernification model and a heat diffusion model to extract the temperature variation over that period. So these temperature variations are given with an uncertainty of 2.5 degrees, and you see that for the very first Downscale event 25, we have a relatively small temperature change of 4 to 5 degrees, but then very soon for the Downscale 24, we have up to 16 degrees temperature changes, which is very similar to what we obtained during marine isotopic stage 4 for this Downscale 19. So that was for the temperature. Now let's have a look on the methane record over that period. And so Todd Sowers already shows some results for marine isotopic stage 3. So here we will have almost the same story for marine isotopic stage 5 with some complication I will show you. So this is the EDML methane record. And plotted on the same age scale than the North Grip ice delta 018 record. And what you can see is, let's say, perhaps now classical features, is that for each Downscale even the very first one here in North Grip, we have an associated increase in methane. And what should be noted now is that, of course, the amplitude of the temperature change that we record in Greenland, and that has been shown in the previous slide has nothing to do with the methane change. So, for example, for Downscale 24, we had a 16 degrees temperature changes, and indeed here we see a very high change in methane. But if you look at the Downscale 19, you see that we had, again, a 16 degrees temperature changes, but we have nothing very significant on the methane curve. So that's the general features. Now let's look at the phase relationship between temperature and methane. And for that, let's have a look on the high-resolution methane measurement over the North Grip ice core. So it's now on a depth scale with the ice delta 018 record. And so you see exactly the same the same thing. So we have here this Downscale 24, and correspondingly we have this very significant increase in methane. To see the phase relationship between temperature and methane change, it's not a good idea to compare ice delta 018 and methane on a depth scale, because we will have a shift due to the firm depth, because this is recorded in the air bubble and this is recorded at the snow surface, let's say, the change. So the best thing to do is to compare temperature marker directly in the air, that is to say the delta 5010 that I showed you before, and the methane. And if you look at the results here, and again that was shown by Todd Sowers 2 days ago, you see that for Downscale 24, this rapid increase in methane is exactly at the same depth, well, according to with the sampling resolution uncertainty, than the peak in delta 59. So that suggests that for Downscale 24, as it has been observed for many of the Downscale even of the last glacial period, we are almost in phase for the methane increase and the rapid temperature increase. However, if you look at the first Downscale even, so this Downscale 25, you see that things are different. You see here on the depth scale this increase in ice delta 018, and you see that on the same depth scale the increase of the methane is on a shallower depth. And this strongly suggests, well, it cannot be otherwise, that the methane increase was clearly after the temperature increase for this first Downscale event. So it really seems that here at the very beginning of the glacial period, we had different climate mechanisms, perhaps, than for the other Downscale even. The last thing that I wanted to show you is the intra-Downscale variability. So here, over Downscale 24, it's very interesting to see that we have first a plateau with stable ice delta weighting value, and then we have two cold spells. And those two cold spells, they are not, they are real climatic signal in Greenland, because we can find them in the Delta 59 record, and we can see as well that they are recorded, at least the first one, in the methane record. So again, here we have something probably very global, and I don't know if it's a good idea, but we can exactly draw a parallel between these cold spell occurring during the plateau of ice delta weighting with what happened during the 8.2 kiloyears event. So again, we have a stable ice delta weighting period with a small shift in ice delta weighting, exactly the same amplitude that we observe for the interstadial phase of Downscale 24. And it's for the methane and Delta 59 measurements that were done by Takuro Kobashi, we have almost exactly the same amplitude. So same duration and same amplitude for several parameters. Now, the last thing for Greenland record I wanted to show you is the variation, the rapid variation of atmospheric delta weighting. Atmospheric delta weighting, that is to say delta weighting of oxygen that is trapped in the air bubble. So this is a little bit tricky parameter, but it is mainly influenced by photosynthesis and respiration that are, of course, the main sink and source for the oxygen cycle. And it can be shown that actually the main variation of delta weighting of O2 are due to variation of leaf water because delta weighting of leaf water will be transmitted to the oxygen during photosynthesis. Leaf water delta weighting is something that will vary a lot. Here you have a map for present day. It will vary a lot because of change in the meteoric water delta weighting and change in humidity. So mainly it will decrease toward the high latitude. And what we will record in the atmospheric delta weighting is, of course, an integration and of all that, but an integration that will be mainly driven by what happened in the low latitude of the northern hemisphere, because that's the region where we have the maximum biosphere productivity. So I show you here the results of atmospheric delta weighting over marine isotopic stage 5. And what is interesting to note is that in addition to the long-term variation of atmospheric delta weighting that were already described and shown to be strongly influenced by precession, we can also see very nice millennial-scale variation. You can see that here and here. And mainly what we observe is that during the interstadial phase, we have a significant decrease of atmospheric delta weighting. So here the scale is inverted. And we think that this decrease of atmospheric delta weighting have two causes. So first, there is, during those periods, a big change in the low latitude hydrological cycle. So, for example, it has been shown a lot during this conference from speleothem data. And of course, if we have this change in the low latitude, we change the delta weighting of the low latitude that are then transmitted to our oxygen isotopes. And the second effect is the one of high latitude. While we are in an interstat period, we will have more vegetation in the northern region, and so we will have a decrease of delta weighting of leaf water that will be transmitted to the atmospheric delta weighting. So that's the general story. And actually, it can be shown that even for the intra-Downscale variability, we have a small change as well in the atmospheric delta weighting, such confirming that those are really global. And the other thing that we can also see is that for Downscale 25, actually, the story is not the same that for the other Downscale event, because this time the decrease of atmospheric delta weighting is before the warm phase of Downscale 25. So again, here we have something different from this for this first event. Now let's go to Antarctica, and so here we have used the methane and atmospheric delta O18 record both from Antarctica and Greenland because they are global tracer, and by putting together a record of methane and delta O18 of the atmosphere of Greenland and Antarctica, we can produce a common time scale. So that was really the work of Émilie Capron. To do that, and the following slides are as well the results of her work. So we use those tracer, we put all that together, and we obtain on the same time scale the Greenland Antarctic climatic evolution. So you can see something actually very similar to what has been observed for marine isotopic stage 3, is that you have for the different events, we have first a slow increase in Antarctic temperature, then the very rapid increase in Greenland temperature, and then the decrease in Antarctica. So that's, let's say, the classical seesaw behavior. So the first conclusion here is that, well, for marine isotopic stage 5, that is to say with different orbital and sea level background, we have exactly the same seesaw behavior as was observed for marine isotopic stage 3. Again, for Downscale 25, things are a little bit more complicated, and actually we are not sure at all that we can have an Antarctic counterpart to this first Downscale event. Okay. So I will speed up a little bit. So that was the general seesaw pattern, and we can also have a look at what happened at a shorter time scale, that is to say the intra-Downscale variability. And here I just do a focus on two Downscale events of the marine isotopic stage 3, so Downscale 21 and 23, that are characterized by a precursor type event at its very beginning. So this has been already described by Grachev, actually. And here, for the Downscale 23, what is very nice from our EDML Antarctic record is that we have a very high resolution record. And you can see that for the double peak that we have in Greenland, we find it again in the Antarctic record. So it's like suggesting that we also have at the intra-Downscale even scale seesaw behavior. So that for Downscale 21, actually, I must say that we cannot clearly identify it, but we also lack from high resolution delta D measurements in the EDML score. Now, so that was the general, that was the description. Now let's try to be a little bit more quantitative. And here we did exactly the same exercise has been done for marine isotopic stage 3 in the EPICA community paper. That is to see if there is a relationship between the North Creep stadial duration and the EDML change in surface temperature. And so in red you have all the Downscale even for marine isotopic stage 3, and it has been shown that we had like a very, a constant relationship between both. Now let's add the event of marine isotopic stage 5, and you see here that for 23, 24, 20, and 23A, which is the small double peak, we are on the same line, but for the very long Downscale 21, we are off this line, so which suggests that the heat flux from Southern Ocean is really is not constant, especially for the long stadial event. So just to finish with, so we saw what happened during the stadial period, so this Antarctic warming linked to the length of the stadial period. Now let's just have a look at what happened during interstadial period. And here I just want to draw your attention on the very different things that we observe between the EDML and Dome C ice core for this seesaw behavior. So on the Dome C ice core, generally we have like a triangle shape, and for the EDML ice core, we have here something more squared with a plateau during the interstadial period. And even for Downscale 23, you see here that here we have a plateau for Dome C, and here we have a strong increase for EDML. And probably I will stop here. So then that is just from the temperature reconstruction. So you see that here you no more have a plateau for Dome C, but a decrease like the classical triangle shape. But for EDML, you remain with this very strange temperature evolution during the warm phase of the Downscale. And yes, that's the summary of the different results that I've shown now.
Thank you very much, and we have time for questions. Yes, please.
So how confident do you think we can be that the stratigraphy of the North Grip core near the bottom, say from 100,000 years and older, is actually completely continuous?
That's a good question. So I will come back to the graph if you want. So yes, I will tell. So here, probably we can try to use this delta 15N to answer that question. So it's for sure that here, delta 15N variation here and even here really correspond to what we have in the ice delta 018 record. So simply, you take a model of firm densification, you force it by the temperature, well, temperature-like scenario extracted from the ice delta 018, and you obtain the red curve that is very much like the delta 15N record. So one is in the gas phase, the other is in the ice phase, and we have a pretty, pretty good agreement. So that's why we are rather confident that it's not very much disturbed. Well, that it should not be disturbed. So that would be my answer.
Further questions?